surface problem I left off without initial conditions. Here's what I'd like to do. I'm going to take your questions in 1 second, but I want to do a little surface problem. And if you've got one you'd like to see other than this, fine. This is going to be 321. And if you look in your book, this is, in fact, you can read that. So problem 321, and it doesn't matter what problem you do, but I'm going to just show you. This has no initial conditions. It has a voltage source, and it's given as U of t. Then it has a resistor, I think this is R1. It has a capacitor here, and that's got some value C. Then it has another resistor, R2, and it has an inductor, and a value L. And what do they actually want?
So the voltage is 2 U of t.
2 U of t. What do they want out of this one, though?
It wants V of t, which looks to be the voltage over the capacitor.
Right. They want this. They want VC of t. Now, the way we do this, I want you to think back in circuits problems for steady or for constant frequency, like a continuous. If you're at a given frequency, like a cosine of omega naught t plus a phase angle, you didn't write differential equations in solving. You went to the domain where j omega existed. Y'all remember this? It's same here. Instead of j omega, we have S. All right. Now, just for the record, I know the voltage across the capacitor. If I have a capacitor, C, and it has a voltage plus or minus V of t, and this is the current I of t, I know that C times dV of t dt is equal to I of t, given this configuration. You all remember this, right? This is very fundamental. If you're an electrical engineer, this should be second nature. It's like Ohm's law. The relationship between current and voltage in a capacitor in the time domain. Now, technically, we could say that if I could write another equation for this. I could say that if I took 1 over C and integrated I tau d tau from really technically minus infinity, but we'll go from 0 to t, that would be V C of t as well. Either of these two is correct. Do you all agree with me? This is just the integral form of the differential. Now keep this in mind. Now, if I take a Laplace transform of this equation, I'm going to use, it doesn't matter, but yeah, I'm going to use this one. The Laplace transform of this equation. Then this would become I of S, right? Would be equal to C times the quantity S, V of S, right? Minus V of t equals 0. That would be the Laplace transform of that equation. Do you all agree with that? So when we do these problems, this particular problem has no initial conditions. So if it doesn't have initial conditions, we can get rid of this right here. And now we can look at something that's very interesting. Now that I can see, I know that technically impedance, and you can call it Z of S, is equal to V of S over I of S. That's the definition of impedance. Resistance was always voltage over current, right, for an element. Impedance is always, the way you think about it, it's always the voltage in the j omega domain divided by the current in the j omega domain. Here, it's the voltage in the S domain divided by I in the S domain. Now, what is that going to be for this one if it's a capacitor? Well, you can see that this becomes 1 over CS, doesn't it? Or SC. You all see that? What was the impedance of a capacitor in the j omega domain? It was 1 over j omega C. You all remember that? So the impedance is literally the same. Now, if you have an inductor, and I'm just going to tell you right here, an inductor L, there's going to be a voltage across the inductor and a current into the inductor. And the relationship between these is L times di dt of t is equal to the voltage across the inductor. Do you all remember that? Now for this one, if you do Laplace transforms of both sides, I get V of S here would be equal to L times the quantity S times I of S minus I of t equals 0. And if there are no initial conditions, this goes away, correct? Are you with me, everyone? And if that goes away, furthermore, I can say if I look at voltage over current for an inductor, I would have Z of S, and this would be for an inductor, this is for a capacitor, would be equal to SL. So now you're seeing that the relationships are exactly parallel to what you did in your circuits courses if there are no initial conditions. I'll get to things where there's initial conditions in a bit. But first, this is the most common thing you see. So now I replace this with the impedance 1 over CS, and I replace this with the impedance SL. Now I think in the book he gives me values for SC and all that. Don't worry about the values. This is R1, that's R2, correct? Now if you're asked, and this is a circuits problem at a constant frequency, to get the voltage here given a voltage here, oh by the way, since I'm going to the Laplace domain, what do I transform this as? 2 over 2u of t becomes what in Laplace in the S domain?
2 over S.
2 over S, yeah. So I put a 2 over S. Now, if you want the voltage across any element, right, you can do it 4 or 5 different ways, right? You could do what? You could use nodal analysis. You could use you could use loop analysis, correct? Mesh, loop. You could use Thevenin's theorem. You could pull that out, find the open circuit voltage there, then find the actual, what, the impedance, looking back in the circuit, and then you could draw with a Thevenin equivalent circuit. Are you all with me on that? Mm-hmm. You could use superposition. Well, there's only one term here, so superposition doesn't bind anything. But what I'm telling you is you have a toolbox filled with ways of analyzing circuits. Pick your favorite way and go for it, all right? You can do it probably the way a lot of you would do it, I'm guessing. You would say, well, this is one block impedance here, right? And this is a block impedance here. So they're in parallel, right? So I could get the effective impedance of those two in parallel. Are you with me? Then I could add this R to it, agreed? Then I can say, once I have that, I have the net impedance that this voltage source is seeing. And then I could get the current, right? That would be coming from here would just be this voltage source divided by the characteristic impedance looking in. And then I'd say, well, that current's going to split when it hits this node. And I can figure the amount of current that goes here because I take the opposite impedance divided by that plus this impedance and multiply by the current. And now I have the current there. And when I wanted the voltage, I'd multiply the current by the impedance, which is 1 over CS, and I'd have the voltage. That's one way to do it. You get the right answer. Another way is you could say, well, since I want the voltage here in the first place, why don't I just ground this? Now, this, by the way, is usually the quickest way. This is going to be nodal analysis, all right? What other voltage do you know? I need to know this voltage. Call it just V of S. And call this, yeah, just V of S. That's what I'm after, isn't it? And now with nodal analysis, what do? You assume a current. I'm going to erase this. I know sometimes I'm messy and I don't mean to be, because I know it's important. But I'm trying to make sure I make these points. That's just, is everybody with me? And this becomes V of S now. This is just V of S is across there. You all with me on this class? Ground means 0 volts too. So if I want the voltage here, you remember with nodal analysis, what does it say? It's Kirchhoff's current law. All the current into the node is equal to all the current out of the node, right? This is the current in. I'll call this I1. I'll call this I2. And I'll call this I3. Now I'm going to just write this as, you know, with circuits has to be like second nature because in electrical engineering, electrical and computer engineering, maybe 1 or 2 classes in processing and fabrication, you don't see circuits. Even then you see it. You see it everywhere. It's ubiquitous. You can't get away from circuits. You got to know circuit analysis techniques like the back of your hand, maybe better even. So for this one, I've got I1 is equal to I2 plus I3. I can do it, you can do it anyway. If you want to do it with loop, do it with loop. But find what you're comfortable with and use that method. Now what is I1? Well, I1 is, and remember I have to put a ground there, would be the current through here would be the voltage on this side minus the voltage on this side divided by R. Do you agree with them? So that's going to be 2 over S minus V of S divided by R1 would be equal to I2. Now what would I2 be? It would be V of S is on this side, 0 is on this side, correct class? V of S minus 0 divided by 1 over CS. So it's V of S over 1 over CS, or really times CS, right? I can say it's times C times S. If it's 1 over CS, it's times CS. Does everybody agree with me there? Then it's going to be plus this current. Well, that current is going to be what? That's going to be V of S, or it's plus, pardon me, plus V of S, right? And then it's divided by SL plus R2. Agree? All right. Now, at this point, what we need to do is break out VS by itself. How you do it's up to you. I'm going to do this on the board, and you don't have to write this down. Just play with me, all right? I want VS by itself on one side. So if I multiply by R1, I get this. This is CS, so now it's going to be R times C times S. And this is going to be R here, right? Correct? Now remember, I'm trying to break out V of S by itself. Now, what I'm going to do, let's see, I'm going to take this to the other side. So I'm going to get V of S over here. All right. And now what I'm going to do is something, because I'm going to have to multiply both sides in a second by SL plus R2. But before I do, I'm going to divide everything by RC. So that gets rid of that, and I get a 1 over C here. And then I divide this by RC. And I divide this by RC. So it's 2 over RCS. Okay. And now what I'm going to do, I'm going to first pull out the V of S over here. So if I pull out V of S, and I make it just come out, then I'm going to be left with this. Y'all see what I'm doing here? Now, what I'd like to do before I do anything further, I'm going to multiply both sides of this equation by this term. And the reason I'm doing it is because I don't want any 1 over things down here. Are you with me? So if you do that, here's where I've got to expand it a little. I'm going to have V of S. Now I'm going to have S times the quantity, C times SL plus R2. Then I'm going to have plus 1 over C. Then I'm going to have plus C times SL plus R2 over RC. Over here, I'm going to have 2 times the quantity C times SL plus R2, and it's divided by RCS. All right, the only thing I've done is try to make you see that I just did a multiplication by that. Now I try to simplify it. So I start with this term. You all see that the C's cancel right here, right? I'm going to let the C's cancel. And then I'm going to bring the 1 over R up top, right here. It's all right. Over here, what do I got canceling? Well, I've got a C canceling there, right? Correct? You with me, class? Now you can see that what I'm trying to do is get it to a point where I can manipulate it, where I can get the coefficient of S, the highest power of S, whatever it is. That's what I want, and I'm going to divide through by that. Now, if you look here, I've got S times S, that's S squared, right? When I take a look at this term right here, this could be replaced by S squared LC plus, and then it would be SCR2. So this could be replaced by S squared LC plus S times RC2. Here, if I take a look at this, remember that's S right there. When I look at this, if I take this and I divide individually through here, is that R1 or R2? I forgot.
It's R1.
That's R1?
Yeah.
All right, so then I could get SL over R1 plus, and then it would be R2 over R1. See where I'm going with this? Now, here's the thing when you're doing this. You want the highest power of S over here to be, I mean, you want the coefficient to be 1, so you're going to divide everything by LC in a second. But before I do, I want you to just understand where I'm going with this. Ultimately, I'm going to take this term and divide this whole thing and divide everything by it, right? So it'll be appearing in the denominator of this side, right? That's the reason I'm trying to get it nice over on this side. When I take a look at this, now I'm going to divide everything by LC. So I'm going to put LC over here. That goes away. And then I have, oh, was that C1 or C2? Does anybody remember?
There's only one C.
Oh, okay, that's good. So this is divided by L, thank you. And this is divided by LC as well, so now I have LC squared. And this is divided by LC, so this becomes C. And this is divided by LC. And now I'm about ready to go to work here. I know it looks messy. I didn't put the numbers in, but is this R1 or here? Or, all right. Now what you do is this. You see how this and this are constants, right? Y'all with me? This and this, the coefficients can be added together. Do you all see that? Here I have S squared by itself. So this is really going to be a polynomial. I'm going to have V of S times something, and I can just call it this. It's going to be times S squared plus AS plus B. Now don't worry about adding, don't worry about the actual numbers. You have to see that that's ultimately what's going to result. Are you with me? And we could go ahead and say that, you know, when I talk about B, the constant would be this term plus this term, right? And when I look at A, that's the coefficient of, it's 1 over CR1 plus R1 over C, right? And you all see how this goes, right? But ultimately, it's just going to, yeah.
I was going to ask, is that because of the characteristic equation?
Well, also, the only thing I'm doing is I'm taking all the coefficients of S, and I'm just grouping them together as one. Now, I want it as a quadratic, because this one I can manipulate further. I can either, frankly, factor it, most of the time simple factoring, or I can get something where I'm going to get complex roots. I'm going to get, you know, it's minus b plus or minus the square root of 4a, or b squared minus 4ac over 2a. That thing, well, the a in that equation, I make sure it's 1, so I don't have to worry about it. All right, now I have that equal to, and over here, I have this whole thing that's just a function of s, right? Now remember, I'm gonna take this, and this is gonna be some, if you look here for a second, just watch this. You see how these two s's are gonna cancel, right? For that first term, and then you're gonna have 1 over s for the second term. Are you with me? So ultimately over here, you're gonna get some constant k1, right? And it's gonna be divided by, it's just gonna be a constant k1 plus k2 over s. I just want you to, the values for those constants we can get and determine in a second, but that's not important. What's important is that you see the structure of this. Got me on this? Now the next thing you're going to do is divide by this term. So now I have this. And now I have V of S by itself. Everybody with me? And now I use the techniques that I've showed you where you get the transform pairings and partial fraction expansion to get these values. For this one, you can see the first term would be K1 over this quadratic, right? That almost smells like a damp sine wave. And I'll get to that in a second. The second term, I've got this over S plus this quadratic, right? So I'm going to have a pole, I'm going to have K1 over S that comes out of that, plus a second term that's either a damp sine or damp cosine, I don't know yet. But that's what I'm really trying to drive at, without getting to the actual numbers, because you need a calculator to do this. They got values in there that are, like, what's the value for C?
For C, it's 0.3689.
All right, I can't do most of that in my head, all right? the stuff I give you will be you can do in your head. It's like 2 times 1 problems. They're not gonna be bizarre like that. But what I wanted to show you was the way you get at this is by using the S-domain analysis. You turn everything into its equivalent S-domain impedance, and then applying your circuit analysis techniques. This particular problem is a little bit annoying because of the numbers they chose, and but it serves the purposes to show you how to do it. Would most of you do this with nodal or mesh? I'm just curious.
Nodal.
I would recommend you use nodal in most cases. It usually lends itself to the simplest solution, usually, in my opinion. All right, if you want to do loop analysis, you can, but. So that's why we're doing these, we're doing all these forward transforms from V of t to V of s, and then reverse transforms. Once you have V of s, what is V of t that caused it? Because ultimately, all the problems you're going to run into, circuits problems and stuff like this, are equivalent to just solving either a forward or reverse Laplace transform. Now, next. All right, I wanted to get that out of the way before I said anything else. I'll take questions about the homework if you have any. I gave you a whole bunch of problems. They were not hard problems, and I gave you the solutions. And thank you, Lydia, for letting me know that in 614A through C wasn't there, and I posted it this morning. Yeah.
Could you do 6.5 numbers C and D?
All right, let's 6.5C. Tell me what it is.
It's x of s is equal to 4 over s squared minus 5, and they didn't ask you to
4 over s squared, is it minus 5 like this?
no, s squared is in s squared minus 5 is in the denominator.
Hold on. 4 over s squared minus 5.
Yes, and they didn't ask you to solve it analytically. They asked
What
you
are
to
they
find the
looking
poles, and then
No, what are they looking for? The final value or
Final
what?
value.
final
All
value.
right, final value is something, I thought I covered a little of this. Let me just say this. If you want the final value for a function, if I want to know x of t equals, first, the initial value is 0. It's equal to the limit, I thought I proved this, of s going to infinity of s times x of s. That's what happens. Do you remember me doing this? Didn't I do initial and final value? Well, I will say, let me put them down. I'll do the proof in a second. I want to finish this. Then x of t goes to infinity, right? That's equal to the limit right here as s goes to 0 of s times x of s. Now, I want to just tell you about these two things. I'm sorry, I thought I did this. These are trivial things to prove, and I will, well, relatively simple to prove. But the reason that they're doing this is to get you familiar with, if you look at an equation, and you want to see if that thing's actually going to be something that's stable. Now, I didn't spend a lot of time with this yet. Thing that's stable is not going to go to infinity when time goes to infinity. Anything that's going to infinity, a voltage, current, anything measurable like that means the thing blows up. That's what it means. It's not stable. If it goes to a constant, it's okay, even though it's not preferred that way. If it damps to 0, that's the one. That's the one you want. That's very stable. It's unconditionally stable solution. Just think of this. If you had a current source and you put a capacitor across it, and the current source was constant with time, what happens to the voltage across that capacitor? Goes to infinity, right? And what does that mean in the practical sense? It's going to short out through the dielectric and destroy the capacitor eventually. It's destructive. That's an unstable system, as simple as I can put it, all right? Stable system would be something where you've got a battery and you flip a switch and you have a capacitor and resistor and you want the voltage across that capacitor when it was 0 initially. Well, the voltage at t equals 0, 0, but it will gradually grow at the rate of a time constant 1 over RC until it's charged to the value of the battery. That's a marginally stable system. Now, a system that's because the voltage doesn't go to 0, but it doesn't go to infinity either. Now, if you have another situation where all of a sudden I've got a switch closed and I've got a resistor and a capacitor, and it's been on forever. The capacitor has a voltage on it, right? Now, when I open that switch, take the battery out, and I automatically throw in a resistor and shorts it, that voltage across that capacitor is going to go to 0. that's unconditionally stable. Does that make sense to everybody? I'm just trying to give you a kind of a mental picture of what stability means before I spend all the time. Now for this stuff, for these two things, let's do this one. If I wanted to figure that out, first I look at the definition of x of s, right? That's equal to the integral from 0 to infinity of x of t times e to the minus st dt. You all agree with that? That's the fundamental definition. Now, if we let s go to 0, what happens? Well, if s goes to 0, I have this, don't I? Right? Now, if I have s times x of, let me do this. Sorry, I'm getting ahead of myself. I mean, y'all agree with that one, right? Now, and that's really, let's do this, x of t goes to that. If I have dx of t dt, that goes to, don't worry about s goes to 0 yet. That goes to simply s times x of s minus x of t equals 0 minus. Do you all agree with that? Correct, class? Well, what is this transform? That's actually equal to the integral of dx dt e to the minus st dt from 0 to infinity. I hope you understand that this is the function dx dt that's put into that definition. Y'all see what I'm doing here? I know that is the transform of it, but this is where it came from. All right. Now, if I take a look at this, and now, right here, I'm going to take the limit as s goes to 0. I want you to see what happens. When s goes to 0, just watch this for a second. You all see when s goes to 0, this is e to the 0, doesn't it? E to the 0 is 1, right? Agreed, everyone? Now, when you integrate the differential of a function, you get the function. So this is going to be x evaluated at infinity minus x evaluated at 0. Do we agree with that? Guys? I mean, if you, dx dt times dt is dx, right? Dx integrated is x, evaluated at the limits, correct, class? It's straightforward, it's obvious. Now, when you look at this, what happens? I've got sx of s minus x of t equals 0. Well, that's x of t equals 0 right there, isn't it? Correct? So just get rid of it. And what do you see? In the limit, as s goes to 0, I can find the final value of x of t by multiplying s times x of s and letting s go to 0. Do you all see that now? You can look back through this. It's really not that hard. What you're doing is just, you're doing a little manipulation of some formulas. Are you with me on this one, class? And by the same token, you can get the other one right here. All right. Only then you're going to let s go to infinity, and the only thing different about it is you're going to take this integration right here with the e to the minus st. I'll put it back in here. And then you're going to let s go to infinity. Well, at infinity, e to the infinity is 0, right? So technically, this is going to not exist except for one point. This is a mathematical kind of trick. This is going to be 0 minus, and this is 0 plus. This is just where you go from the threshold, where you go just before it was on to just where it is on, right? When you do this differential integral, this goes away because you're going to only be about 0. And when you get this, you're going to get x at 0 plus minus x of 0 minus. And we take the limit as s goes to infinity on that, right? Then you're going to get not x of infinity, but you're actually going to get x of 0. Now, you can spend time with this after class. I don't spend much time on this because, frankly, I never use that. Only time I ever use this, and I'll tell you the real trick, I always look at the highest power of s in the numerator versus the denominator. If the numerator is greater than or equal to the denominator, I've got to show you some tricks in this. I do division, because that won't be a stable solution, and I'll show you how to deal with this in a bit. But for now, these two things are the only things that are important to know. So back to your question. They want to know the value of this function of x of t. Some x of t created that. At t equal what? Infinity or 0?
Infinity.
All right, they want to know as t goes to infinity what it is. So we just do literally what it says up there. I go ahead and I take the limit. If t goes to infinity, s goes to 0. Remember that. They're opposite. Of what? Of s times x of s. So it's s times x of s, or times 4 over s squared minus 5. Follow me on this, class? Now, as s goes to infinity, the way you evaluate something is this. If as s goes to 0, right? Correct? If s goes to 0, 0 times 4 is 0. 0 minus 5 is still minus 5, right? So I don't have a 0 over 0 problem. What in fact I have is 0. So this will be equal to 0. Is that the answer in the book or in the solutions?
It says no stable value.
Wait a second. Okay. I'm sorry, I didn't get to this. The reason it's unstable.
Excuse me. I think you write the wrong problem because
What is
the
it?
5 should be the s.
Oh, this is supposed to be 4 over
S squared minus S.
4 over 5 minus s squared?
No, the s squared minus s.
On the bottom, s
S
squared?
squared minus, oh.
Is it s squared minus s?
Yeah.
Oh, well, that's completely different. Now for that one, if I take this and multiply it by s, if I take s times 4 over s squared minus s, really what I have is what? I have s minus 1, don't I?
Mm-hmm.
Now when I have that right there, and I take the limit as s goes to 0 here, well, this is a little tricky on this one. Multiply s times that, and the limit is s goes to 0. This would say it would go to 4 over minus 1 or minus 4, correct, class?
Mm-hmm.
But here's the problem with this one. These poles are in the right-hand plane. Now let me I'll just show you this in a second. If I take a look at this, first the transform. If I have s plus a, and I want to go back to the time domain, I know it's e to the minus at times u of t. Correct, class? Mm-hmm. Well, if it's s minus a, then this becomes plus. If a is a constant, positive constant, all right? Now what happens to that value as t goes to infinity? It goes to infinity. In the book, he probably said he looked at the pole here, and it was in the right-hand plane, so it's unstable. Now here's how you tell. When I look in the s plane, and this is the j omega axis, and this is the real axis. So this is like the sigma axis, and this is j omega. And remember, s is equal to sigma plus j omega. When you plot poles, you all see the pole here is at 1. With me? Mm-hmm. So you put an x there, and that indicates it's a pole. Now any pole in the right half plane means any pole on this side of this drawing means it's unstable. Poles in right hand plane, unstable. And you don't even have to do this, but technically for this one, they want the value as t goes to infinity of this. So if I multiply by s, I get this, and if s goes to 0, I get minus 1/4. And that's one of those that doesn't seem to show up. That doesn't seem to expose the property, but the pole does. Is that what they say? They say they look at the pole, or they do it?
I think they said they look at the pole and then.
But that's the way you tell, all right? It's because the fact is that pole's in the right half plane. And unfortunately, when you do this one by rote, if you multiply this by s, and take the limit as s goes to 0 here, well, if you didn't do any manipulation, I would have 0 by 0, and that's undefined. If you manipulate it, you get s minus 1. Now that does not go to infinity. That goes to minus 1/4, and it doesn't reveal the nature of this. So the only way you can see is by a pole plot right there. Remember that. Any poles in the right half plane could be up here, could be here, anywhere in the right half plane means this function is unstable. Okay, everyone? And that always, what it really means is systems are going to grow to infinity. As time goes to infinity, whatever value is. Yeah.
So On your answer for this one, you said pole at s equals positive 1 implies that x of infinity is not infinite?
What?
It
It is infinite.
Yeah.
It
The
is
answer says
infinite.
not infinite.
Mhm.
No, no. I think that, unfortunately, this right here goes to, this has a pole in the right half plane, but the fact is this, this is one of those things where I'm gonna have to, I need to go through a couple more Laplace transform solutions of this. The actual one was s squared minus s, right? 4 over s squared minus s? Well, why don't we do that, just to show you. You know, I'm sorry about that. This doesn't go to infinity. I was saying something wrong here. This I was taking as just the functional form x of s. It's not x of s. It's x of s times s. Let me do a redo on that. Make sure I'm clear on this one. All right, first the function s over, it is s, is it? Or no, it isn't. It's just s squared minus s, and this is 4, isn't it, class?
Yes.
All right, that's the function x of s. So let's first just do the expansion and find out what the Laplace transform is. Then I'll talk my way through the rest. When I take a look at this, I can see this is really equal to 4 over s times s minus 1. You all agree with that? Right? You just factor on s. That's equal to k1 over s plus k2 over s minus 1. These are simple poles. Do you all agree there? All right, what's the value of k1? Here you cover this up, right? Then you evaluate the remainder at the pole, which is s equals 0, correct, class? That value is going to be 4 over minus 1 or minus 4. So this is minus 4. Now what's k2? Well, k2, I cover up s minus 1, and the pole is at s equals 1, right? So that's 4, isn't it? So that's 4. Now, what's the inverse transform of that? If that's x of s, I could say my x of t would be what? Well, what does this go to? Minus 4 over, or minus 4 times what? U of t, right? 1 over s is u of t, right? You've got to know the pairings. What's the second one go to?
Negative.
E to the what? E to the t u of t, right? Does everybody agree with me there? Are you with me? Now, when I look at this, what is this function going to as t goes to infinity? It's going to be infinite. Do you agree? I mean, it's really, unless there's an s up here, this is the problem, isn't it, class? Right. Then that's going to infinity. That's unstable. And if you have this function and you multiply it by s, if you have this s squared minus s, and I multiply by s, and then I take the limit as s goes to 0, it says it goes to minus 4, doesn't it? Does he show this in the work? But you actually don't see it, and I don't know, I'm gonna level with you, I don't know why this doesn't show the truth, and I'm not sure why. I'm gonna look at that when I'm done with this class. But I can tell you, if you do the inverse transform of this, you can see that that's unstable, right there. All right, and so that's the way you can see it. And the minute you take this and take a look where the poles are, the minute you have a pole at the positive, s equals anything positive, any real value is plus, you know it's unstable. I'll have to look at that once more. What's the next one? Go ahead. This is an initial or final value. Did they want the initial or final on that? They want the final?
That one was the
I think that
final.
was the final.
What's the next? I mean, was it initial or final for the next? Which one was it?
we can do 6.14 question F, which is the initial value, I think.
Initial value of what's the
So,
function?
It's d squared y over,
What, D?
oh,
S squared.
that. What's this?
Which one? It's a
This is
differential.
yeah.
So,
Okay, that's right. Yeah, these are more important. Go ahead.
second derivative of y with respect to t plus, is that a 6?
Yeah,
6
it's a
times
6.
the first derivative of y with respect to t
Go ahead.
plus 9 times y.
Y of t equal?
That is equal to sine of 2t
U of t.
u of t.
All right, now this is more or less a differential equation related to a circuit. Did they give initial conditions or not?
They're both 0.
Thank God. All right, no initial conditions. The minute you got no initial conditions, life is good. And here's why. I'm going to take the Laplace transform of this entire thing. Now work with me on this, and you have to know these. Laplace transform of a second derivative without initial conditions is just s squared times y of s. So here this becomes s squared times y of s. All right, does everybody understand that? Now, the first derivative of y with respect to t, the Laplace transform, is sy of s with no initial conditions. So this is plus 6 times s y of s. Finally, the last one is 9. Well, 9y of t, the transform of that is just 9y of s. Now I got to take the transform of the sine of 2t u of t. And that's 2 is like omega naught. That's omega naught over s squared plus omega naught squared. So this would be omega naught is 2 over s squared plus 2 squared, or 4. So that's my Laplace transform. Y'all with me? Now, when I go ahead and I factor out the y of s, I get this. I get s squared plus 6s plus 9 equal to 2 over s squared plus 4. I think you all see what's going on here. Now, when I take a look at this right here, I'm going to divide it into this thing, so I get y of s is equal to, and here it's going to be 2 over quantity s squared plus 4 divided by s squared plus 6s plus 9. Now, do we want to get the inverse transform of that, or what are they asking for this one?
I think.
Inverse
I'm
tra-
trying to find the inverse transform.
All right.
Y of s. Capital Y.
Is that what it said?
It says
Yeah.
use Laplace transforms to compute the solution.
Of what? The y of t? All right, they want the time to me. For this, we're going to have to expand it in a couple of ways. First, I want to just take a look at this for a second. And I'm going to say, does that look like something that maybe could be factored? Does everybody see it's s plus 3 squared? So I'm going to put that up there. This leads me into a proof too. I'm digging here to get all this stuff in. So I'm going to just factor that as s plus 3 squared. Everybody good with that, right? So, and you have to be able to see these pretty well. So this is s plus 3 squared. Got that? Now what I'm going to do is this. I'm going to go ahead and expand. The one that's going to be tricky is this right here, the s squared plus 4. But what I'm going to do is expand this. I'm going to take a over s plus 3. That's the first pole is just s plus 3. Then I've got to take b over s plus 3 squared. All right. Then I'm going to take c over s squared plus 4, and I'm going to show you how to do this one. I'm going to expose you to a few things when I'm doing it. All right, so the first constant I'm going to go get is going to be b. And the reason is because it has the pole squared. It has a complex pole. It's got s plus 3 and it's squared. So the way I'm going to explain this to you is if you multiply everything by s plus 3 squared, just go with me on this one. I go s plus 3 squared. Now that gives you an s plus 3 here, and this is going to be s plus 3 squared. It gets squared. That gets rid of this, and then you're going to have s plus 3 squared. Follow me? That's the result. I'm going to go ahead and erase that here so you can just see this pretty clear. That cancels, right? Now I want to get b. The pole s plus 3 occurs at s equals minus 3. Do you all agree with me? At s equals minus 3, you'll notice one thing. Because this is s plus 3, this is s plus 3 squared, it's really s plus 3. Well, when s is equal to minus 3, a goes away. Do you all see that? When s is equal to minus 3, this term goes away. Follow me? So you're just solving for b. Now, when I get b, I let s be equal to minus 3, correct? Minus 3 squared is 9. 9 and 4 is 13, right? It would be 2 over 13. Y'all see this, class? Right? Just take s as minus 3 and square it. You get 9, right? 9 and 4 is 13. Then I have 2 over 13. So I can make b 2 over 13 over s plus 3 squared. And the other terms were I had a over s plus 3, that was the single power, and I also had some constant c over s squared plus 4, right? All right, now the next term we're going to get is a, and this is important you see this. There's a couple ways to do this, and I'm not going to try to go faster. I'm going to try to show you this in terms of the derivative method. You've had all this before in your differential equations courses. You probably don't remember it that well. But whenever you get a higher order pole, this is a second order, here's what you have to do. Come over here, and if I say that I have some function f of s on top, and then I have something with a higher order pole, I'm going to just take the second order pole. S plus a squared. I know when I expand this, I'll tell you what, let's not make this a constant. I mean a function of s. I'm just going to call this k1. This has got to be expanded as some a, first constant, over the first pole, which would be s plus a, plus b over the second pole, s plus a squared. Matter of fact, what I am going to do, I am going to make this f of s for a reason. Now, this is important to follow me. The first thing you do is you get b. So you would cover this up and evaluate f of s at s equals minus a. You follow me? So I'm just going to put b would be f of s equals minus a. Now, once I have that, I want you to listen to this. Now I'm going to multiply both sides of the equation by s plus a squared, the highest power. This is very important. Follow me on this? So when I do this, I get rid of this, don't I? Up here now I have s plus a as a result, and then I get rid of this. Everybody with me? Now remember, that's a constant, isn't it? I'm just going to put it as a constant. I'm just going to call this some constant. Call it b. What I want to do is evaluate a, and this is a derivative method for doing that. What if we take a derivative of both sides with respect to s? Now we get f of s ds is equal to a, and all the other terms go away, right? Now that was based on a pole s equals minus a, right? Now you evaluate this derivative at s equals minus a, and you get the constant, capital A. That's the derivative method. In the book, he shows you this. The method that you probably use, because it's easier, was this. If you had, I mean, did you remember this vaguely? How many remember that derivative method? Do you remember a little? I'm going to tell you, it's common. I use it because it frankly gets to the answer pretty quick on most functions. I mean, things like e to the minus 5t, u 5t, I can take that, or I'm sorry, if I have something like just s squared, the derivative of that is simple to get 2s, stuff like that. All right, now, here's the way you would probably get it. If you had a function f of s over a higher order pole, s plus a squared was equal to some constant a over s plus a, pardon me, A plus B over S plus A squared. What you probably did is this. You took this equation and you multiplied everything by S plus A squared. So you got this. You had A times S plus A plus B, and you had f of s over here, right? And then what you did is this. Now f of s is really going to be a polynomial, so I'm just going to show you. So it would be some a, or let me put it this way. Let's say it's equal to, am I over? I'm sorry, just hang on for 1 second, I'll be done. 5s plus 6. And I want to know what these constants are. I want you to follow me. Well, I just look at the coefficient of s over here. It's 5, right? What's the coefficient of s over here? It's a. A becomes 5. It's a no-brainer, right? Got me on that one? Now what did you do next? You looked at the coefficient of that were constants. Over here, it's going to be 5a plus b equals 6. I know a is 5, don't I? I mean, I'm sorry. Yeah, I put the 5.
You know what A is.
Pardon me?
You would know what A is.
25 plus b equals 6.
That's right. 25 plus b equals 6, therefore b is 6 minus 25. Do y'all follow me? That's the way you did it. You equated the powers, the coefficients of the powers on s, and that's an easier way. I'm sorry I'm out of time on this. I was really trying to do my best to get a few more problems in. For Friday, you're going to get a quiz on Laplace transforms. It's probably going to be a circuit problem. You're going to have to solve a circuits problem. Okay? I'm fair about that. And so it means it's either a differential equation or a circuits problem, which means, frankly, if it's a circuits problem, at least at this point, it will have 0 initial conditions. Can I be clear? All right. See you Friday. And sorry I got hung up. Hey, are there extra quizzes
I
back
was
there?
thinking about that. They're right there.